In earlier chapters, we examined functions that describe the total amount of a quantity. Cost is the total amount of money needed to make a product as a function of the number of items made, and we denoted that by C of x. Revenue is the total amount of money received from selling a certain number of items, and we called that R of x. Profit was simply the difference between those. And from these quantities, we were able to calculate rates of changes of the quantities by taking the derivative of the functions describing the quantity. For instance, if we had C of x equals 50x plus 1,000, we could take the derivative and get C prime of x, which in this case would be 50. So this was simply the marginal cost, and it was a constant. Suppose that we are given the rate of change, and what we want to find is the total quantity. In other words, if we're given the rate, if we're given the derivative, C prime of x equals 50, what do we need to do to figure out the original cost function, 50x plus 1,000? Suppose that I'm given capital F of x equals x to the 6th plus x cubed plus 5. I can take the derivative of that to get capital F prime of x equals 6x to the 5th plus 3x squared. We could go backwards by realizing that we have the derivative f prime of x, which is 6x to the 5th plus 3x squared, and we can work backwards to get what capital F is, to undo the derivative. And certainly if someone gave us this x to the 6th plus x cubed plus 5, we could certainly recognize that yes, this is the proper undoing of the derivative. So what we're going to be talking about is the antiderivative. If capital F prime of x is equal to little f of x, then capital F is the antiderivative of little f of x. In other words, if we're given a derivative and we find the function without the derivative on it, then that is the antiderivative. Going from f to f prime is derivative, going back the other way is antiderivative. Now, the first thing that comes up is, does every capital F prime of x have a unique f of x? In other words, if we know the derivative, is there only one antiderivative? Well, suppose we're given the derivative f prime of x that we see down here below, that f prime is 3x squared. What must be the antiderivative of that? Well, I think most of you probably know right away, having done enough derivatives, that we have a rule for the power rule which says the derivative of x to the n is n x to the n minus 1. So if we match up 3x squared, our derivative, with the result of the power rule, which is n x to the n minus 1, we know that the n minus 1 must correspond to the 2, so n must be 3. So that tells me that the derivative of x cubed is 3x squared, so the antiderivative is x cubed. Capital F of x is equal to x cubed. So if capital F of x is x cubed, the derivative of that is 3x squared. If capital F of x is x cubed plus 1, the derivative of that is also 3x squared. And x cubed plus 10, that derivative is also 3x squared. X cubed minus 99, the derivative of that is also 3x squared. So in fact, we have all of these functions whose derivatives are 3x squared. In fact, any x cubed plus some constant is going to give that exact same derivative 3x squared. So when someone asks you to find the antiderivative of 3x squared, you're going to get many different possibilities. In fact, if f of x and g of x are both antiderivatives of the function little f of x on an interval, that means that there is a constant such that when I take f of x minus g of x, it's equal to that constant. So two antiderivatives of a function can differ only by a constant. That constant, c, is called the integration constant. For instance, if capital F of x is equal to x to the 10th minus x to the 5th plus 7, and capital G of x is x to the 10th minus x to the 5th minus 1, those two functions differ by a constant. If I were to subtract f minus g, I would get 8. And that means they're both antiderivatives of the function 10x to the 9th minus 5x to the 4th. So if f of x and g of x only differ by a constant, this means if we looked at their graphs, they'd look exactly the same except for a vertical shift. We'd expect this to be the case since they both have the exact same slopes. So by shifting functions up and down, we don't change the slopes, and that means our functions differ by a constant.